Okay, so I'm going to start doing the introduction while everyone else starts joining the seminar today. So first of all, well, good morning, afternoon, it depends where you are. Thank you everyone for coming, and especially thank you, Johannes, for joining us today in our seminar series. So today we have Johannes Brandstetter as our speaker. He is the leader of the group of AI for data-driven simulations and the Institute for Machine Learning in the Johannes Kepler University in Linz. And also he is a co-founder of one of the leading startups in Europe, MEAI. And he's basically working in the bridge of data-driven methods in science and engineering. And today he's gonna present to us one of his very recent work that hasn't been published yet. So very exciting for us. And I think the floor is yours from now on. Thank you so much for joining us today.
Thank you very much for having me and for the kind words. It's a pleasure to be here, and it's a pleasure to talk about what we're doing. The nice thing about doing academia and industry is that you can basically get inspired by what drives industry and try to do it in academia and try to get the novelty of academia in industry. If you stop doing this, kind of you lose track. So in a way, we are in the middle of experiencing some kind of the first momentum in this AI for engineering. So it's the first time that both venture capital companies and startups, venture capital funds and startups, and everyone starts to feel a momentum and things are happening. But especially when the first wave of momentum is going to happen, it's not clear where this is going. Everyone just realizes, okay, there is a momentum, there is a huge potential, but it's not like language and vision where it's very clear how to train large models and probably also clear what to do with them to some certain extent. It's a very big unknown. So what I talk about is my personal view of what I think could be a game changer, or what could be a possible realization of new type of modeling schemes, very much related to what we're doing at MEI, also showing some of the models which we will release next week. So I call this large engineering models, and jump right into the topic without further ado, before afterwards giving a bit more context. I'm assuming, or strongly assuming, that you are familiar more or less with like typical engineering workflows. Very roughly speaking, for me, an engineering workflow can be split into two parts: a design part and a simulation part, which is, I think, very different than other domains, especially, for example, material science, and then all other bio and life science disciplines, where validation usually happens in the lab and the design part is usually done by some generative aspect, being a neural network or other generative aspects. But in engineering, we usually tend to evaluate designs on our computer. And this means historically that the whole software complex has been split into two fields, into designing tools and into simulation tools. And if there are two types of tools, then there's lots of interfaces, how you take a geometry, a proper representation, a proper NURBS representation, how you clean this representation, how you get a mesh out of this representation, and then finally how you run a simulation. This is the usual validation circle, how a design engineer gets physics validation. What most people usually try to do, they build surrogates, especially surrogates for the numerical simulation part, which is a certain part in this design cycle where you can apply a surrogate. What we are trying to do is to give validation directly on a design. So this idea, and I will later tell you where this is coming from, should be a direct feed. Is there a question?
I think one of the microphones was open, but it's fixed now.
And just for everyone sees that we're on slide 2, right? So usually this is also a typical.
Yeah. Yeah.
Okay, cool. But this is usually a Teams problem. Okay, we assume. So what we call large engineering model should be a direct feedback to every designer. To make this a bit more haptic, we built our first model for injection molding. And injection molding is the process of, especially plastic injection molding, is the process where you inject the mold, like a liquid, into some form, some geometry, and then the liquid fills the geometry, starts to cool down, and starts to produce things like a smartphone cover or contact lenses or whatnot. And this injection molding is where we settled approximately a year ago to build the first model which does that. And the idea is to have a model where the injection model engineer can put in any geometry, and the model gives basically the physics back so that you skip all the immediate steps. That sounds, I don't know how clear this is to you, so the best is to show an example. What we did is we partnered with the company, and the company is called Simcon. It's a relatively small injection molding company. They produce software for simulating injection molding processes. And very nicely, they have the full value chain in-house. So they have the value chain CAD mold, which is the design tool for injection molding software. They have all the tools which does all the interfaces, and they have the tools which do physics modeling. And in our basically model, you can choose different geometries, different plastic materials, different temperatures, different flow rates, place the injection gate, so where you inject the plastic into the geometry, and then you can basically run the physics immediately. And then you can validate and basically whatever a designer is doing. And this is the type of modeling which we envision, that instead of running all these different circles, you can get this physics feedback basically on the go. And we will release this model next week. So there will be a web page, and you can do all this stuff which I show you here online. You will basically make all our GPUs go hot in the background. Let's see when our system breaks for the first time, and you can try live what works and what doesn't work. I also want to say here that this has like a very challenging part. That's all the things you see on the left, like all this variation from different geometries to different material properties to different where you place the injection gates. Like this is a tremendous amount of variability. What is the simpler part here is the physics, because the physics is rather linear. So the way this mold goes into the plastic is modeled in a linear way, and therefore modeling the physics is I would say and the least challenging one. The more challenging one is to get this generalization. So this is our first model, which gives injection molding engineer, and believe it or not, there are quite a few people who care about how to place these gates and so on and so forth, a direct design feedback. And this is basically what we are building since quite some time. And I tried to build this talk around the following clarifications or the following ideas, where we actually coming from, where these ideas are coming from, and why, or what was the intrinsic motivations, the big challenges along the way, both past, present, but also future, and what I personally think can be built now that we have built this first type of model, which we call a neural mold, because it's a neural version of injection molding process. Actually, the ideas come from weather modeling. I've spent quite some time at Microsoft a couple of years ago, where we tried to build weather foundation models, because weather foundation models are tremendously helpful for making better prediction, faster prediction, asserting when a catastrophe is happening, and so on and so forth. And there's quite some hype about machine learning and weather forecasting. And in weather, we basically are we ran through three phases, which are quite familiar to every engineer. We ran through the analytical phase, where Navier-Stokes equations were written down, couplings with atmospheric basically models were done. And then we had the numerical age, which was basically discretizing Navier-Stokes equation until the weather models in the 90s. And believe it or not, these models are still used and basically are the state of the art still in weather modeling. And then there is this AI age, because it turns out there is an abundance of weather data and you can train very nice models on that. And so people started to develop quite a few of these approaches. I was personally involved in two types of models from Microsoft, Climax and Aurora, which were trying to build a foundational intelligence for Earth systems. I always keep saying that weather modeling is nothing else than computer vision on steroids, because weather data is kind of images. So you have high resolution images in either, like if you look at the surface, it's a 2D image, classical image, and if you take the pressure values, so the atmospheric component into account, you have three-dimensional images with very high resolution, and you model this data on these images. One thing to take into account is that this is high resolutional, so loading this data is super tricky, and basically you come into a lot of challenges. But still, since we're dealing with these high resolution images, we can use all the tricks from computer vision, and we can use all the data available. So there were a lot of success stories, and it was relatively easy to come to these success stories. So when weather modeling started, like 2018 to 2019, until the first models which achieved superhuman capabilities in terms of prediction accuracy, they were like celebrated in Nature publications and so on and so forth. I was involved in this project Aurora before leaving Microsoft, which built a foundational intelligence able to model several types of systems. There was quite some hype around that, and there is still a lot of celebrated groups doing this type of models. For me, there was always this one side of the story which was never told, and this is the two sides, or the 2 points of weather modeling. So we have two streams. We have the data assimilation stream, which is the stream where you convert all measurements of atmospheric data, atmospheric balloons, or sea data, or every type of sensors into initial conditions which are placed on the sphere, and then running a forecast on the sphere. And all these weather models were always concerned about running a forecast on the sphere, replacing the second part of this whole chain. And I found this always a bit unsatisfying, because you praise, so to say, the power of AI and what you can do with AI, but you only replace half of the story. So there's a few labs, Rick Turner in Cambridge and so on and so forth, who basically try to directly learn from observations. But overall, it feels like half of the story. And when I started to look into engineering, this was very much what the CRD-CRE paradoxon reminded me of, that we have these people who care about design and everything which is design related. And then we have the people who build surrogates and who take basically a simulation mesh as input. But as an engineer, when you're at the simulation mesh, this is basically already at least half of the job done. So it felt a bit like this. And for me, coming from this weather modeling and seeing basically how weather modeling revolutionized the way or deep learning revolutionized the way how weather modeling is done, I felt a bit like, to have this big impact, you need to have something which works directly for a designer and not something which replaces the simulation engineer. So we set to do this approximately 3 years ago. And as it is always in this type of research, in hindsight, everything looks much clearer. Back in these days, it was like completely blurred and it was very hard to formalize what actually we want to do. But there was always this type of scales we wanted to tackle: model scale, data scale, and problem scale. Model scale basically means that when you run a neural network on a Formula One car, for example, with more than 100 million volumetric mesh cells, this is definitely a different challenge than running a neural network on an image, even if it's a high resolution image. Data scale is the fact that industrial data is very scarce and everyone cooks their own soup, and it's very hard to attack data. And problem scale is the idea that every simulation field is its own subfield and its own splitter field, and there is very little similarities about CFD, injection molding, and so on and so forth. And these were the three types of scales we were tackling. The first, and that was especially handy being at university, was the model scale. So we tried to understand a bit what it takes to use transformers for industrial size problems. I always say, what does it mean to tokenize physics? Because there's a lot of these peculiarities which physics data have, which are not in computer vision. And in the end, everyone knows a transformer is the underlying successful architecture. But what's the right way of how to tokenize physics? That is still very unclear. Especially when you start to think a bit what this type of model should do. A powerful model should work on any type of geometry. It shouldn't be like a simulation mesh shouldn't be a prerequisite for the model to work. It should also work on SDF inputs, STL inputs, any sort of design inputs, because that's what the model should run inference on. It should be able to switch between these representations because the power comes from basically this universality that you can give different designs. They can be an SDF, they can be STL, and it would be very, very cumbersome to start cooking the soup again and again. And there is this big scalability issue, which was always bothering me, that if you want to do Formula One, you need to have a scalable solution. And then there is basically relating to scalability, there's the fourth point, and this is the degrees of freedom. If you write down a PDE, you can basically write down a PDE with a few equations, boundary conditions, initial conditions, and so on and so forth. You don't need so many degrees of freedom, but still you end up with these super big simulation meshes, which you need to, the discretization of which you need in order to get all these derivatives and so approximate. So there's a mismatch between physics degrees of freedom and simulation degrees of freedom, which you somehow should understand in this tokenization. And then there's this multi-physics and even multi-scale aspect. So there's a few, I would say, unresolved challenges in the way we think about these problems. There is this picture we have in mind, and which is kind of the design principle for all of our architectures. It's more a recipe. I mean, there's no formula in it. But I consider like a few aspects which are important, no matter what type of problems you have. The first is usually you can do very heavy subsampling of your data. The reason being that meshes or discretizations are basically used because otherwise numerics would not converge. You don't need this type of fine graining for machine learning models to understand all the concept. Secondly and thirdly, you can use the tricks from computer vision. That is first a local aggregation and secondly a global aggregation. So this is the way you aggregate information. And if you follow these principles, you always end up with some sort of tokenization, which I mean that the devil is in the detail. How to apply that to real world data or to actual data is the hard thing. So this is just kind of the recipe we are following. And the important trick is that we started to write down simulations, not from a particle or mesh point of view, but we treated everything as a field, which gets very clear if you look at this type of simulation. So this is a industrial sized hopper simulation, which is very, very important in Austria in autumn when harvest season is, and you basically you want to know which food is going to rot and which food is running out of the silo. So you're modeling this type of simulations. And what you see on the left is a 500,000 particle-based discrete element method. It's pretty cumbersome to compute. And what you see on the right is the neural network. If you try to model the simulation on the left with some sort of graph neural network where you learn all these interactions, this is a pretty hard training task because you have to get all these interactions right. And if you fail a bit, the model totally goes out of distribution. But if you represent the data in a way that you just treat the full data as a field, and every particle is just a realization of the field, and in that case, we just model the displacement field, it's actually very simple to let the network predict the next time step, because the network only has to predict the network has to learn this continuous representation of the left and predict a continuous version of this on the right, and then predict at certain points. And the network which does this job is like a very tiny network. It has just a couple of million of parameters, and it's very stable to train. And so this field point of view we're using in all sort of formulations. And a classical one is we did this fluidized beds that's already 1.5 years old, which people who do multiphysics, especially DM and CFD coupling, consider one of the most challenging or one of the, let's say, litmus tests for their solvers. So you have on the left particles and they're bouncing. You can think of sand or some other particles, and then you have air blown from the bottom, and the particles in the air, they interact in a chaotic manner. And so basically only look on the upper part. So you have the particles bouncing, and the middle one shows basically the fraction of particles per unit cell, and the right one shows the CFD component. And the trick is now to encode this type of physics in a way that you can easily tokenize it. And it's the same challenge it's the same procedure as before. You come up with a quantity which can be represented as a field. In that way, it's the ratio of particles per unit cell, because this is a kind of a continuous quantity, and then you can tokenize unit cells, and the fluid one is anyway simulated on a three-dimensional grid. And then you have these two type of continuous fields, which you tokenize using standard transformer tokenization. And then you have tokenized representation in which you can run attention and cross attention, self attention, whatever attention you want to use. And so this is just one step further from the what I showed before. First is we treat everything as a field. That helps us to make a clever tokenization. The second one, if you have multiple fields, you just encode each field separately, and you let this field interact in the latent space. The lower and the bottom part here is on the left, the output of the neural network. This is like the isosurface of these volume fractions, because the network is not able to output particles, so it has to output some continuous quantities, and this is basically how you translate from one to each other. And then we basically had these design principles, like null fields, field-based representation, and these multi-branch ideas. And then we started to model CFD, because most public data sets are CFD, and actually our biggest customer, which I show on one of the next slide, is a CFD customer. So we started to think of how to apply these principles to CFD. And there comes the next design principle, or the next observation, that especially in these industrial CFDs, we talk about steady state CFD simulations. So most steady state CFD simulations are either RANs or if there is a lot of compute, like some large eddy simulations, which are still time averaged. And what this means is that you run a simulation, then you average over time. Similar in RANs, you just model the mean the mean behavior of the field. And this means that simulations neglect high frequency components. So you have a lot of low frequency content. And in return, this means that you can that the number of degrees of freedom in a simulation is very different than the number of simulation mesh cells, because there's little high frequency component. So you can actually very heavily subsample these problems. And we use these design principles. So in this typical CFD simulation, especially when we talk about external CFDs or cars and planes, we divide our network into two of these branches. So the one branch which takes care of the volume, and the one branch which takes care of the surface, similar to the particles and to the fluid which we had before. And then we place different tokens on the surfaces using the idea and the finding that you do not need all these 10 million surface cells to represent the full physics, but only a very dedicated subset. And we call these tokens anchor tokens. I show in the next slide how these are selected. And these anchor tokens are basically representations of this geometry. Then you have these anchor tokens on surface and volume, and you can train a model just on anchor tokens. So you train it on a limited information. The challenge is just to use enough information to not throw information away. So it's again this section of like heavily subsampling, and then basically down projecting this subsampled representation into a tokenized version. Then you do cross attention, and you can train these neural networks. The idea is that if you need the full information in inference, so if you want to reconstruct the full surface and then the full volume fields, you add some query tokens. And these query tokens, you can basically add all other tokens on surface and volumes. But these query tokens, they attend to frozen keys and values in the attention layers, and therefore they scale linearly. So you can add as many query tokens as you want. You have a linear scaling, and that means you can easily, if there is need, you can easily run very, very high surface simulations. And that was for us solving, especially for CFD, this problem of these super huge meshes, because we could train on this limited, what we call anchor tokens. How are these anchor tokens selected? This is a different story, but I show you some. I show you what this means in practice. Let's look at the upper plot. So this upper plot shows training losses for different number of anchor tokens, and only look at the colors here. And blue means the model is trained with 4,000 tokens on the surface and in the volume. The greenish means 8 and 16, and so on and so forth. And you already see that if you approach a certain number, in that case 130,000 tokens, both on surface and volume, the loss is not going down anymore. And that means you start to capture all the information. So basically 130,000 selected volume and surface points in different orders is enough to get all these values. And this is so to say was the fourth design principle, that the physics degrees of freedom and simulation degrees of freedom do not always have to be the same. And so this anchor attention is one of our core design principles. And to make this a bit more haptic, this is two of our customized use cases. The one on the bottom left is a Formula One car, where you have, if you run simulations there, you would have a huge number of volumetric mesh cells and a huge number of surface mesh cells. So you need to have this selective representation of tokens in order to really scale this up, because if you want to get the drag and lift predictions correctly, you need the full surface and volume predictions. And the right one is a electrical power grid transformer, which is one of our, I would say, project we are most proud about. And we are modeling these power grid transformers. They are also CFD simulations. They've is very challenging grid because in internal ones they have a lot of windings. This is a partnership which is now becoming public, and we are modeling these power grid transformers with the same modeling type of principles in a way that we have this anchor and volume tokens, and we can do this type of predictions on this huge 100 million plus mesh cells. So this was actually invented for this type of simulations, but done a lot of on cars. So to summarize, we had these different design principles. We didn't solve all, but we came up with a way of at least tokenized physics for steady state simulations, like in this CFD. We came up with a way of how to run inference on these large meshes without losing accuracy, and we had a very nice way of how to do multi-physics representation. Still a lot of challenges ahead for us, especially when there is more turbulence in it and when there is like a larger dependency on geometry and so on and so forth. So this is like definitely an ongoing field of research. The second topic, which is really interesting to me, is what I call problem scale. And problem scale, I don't know if it's a descriptive word, but I very much believe that whereas in simulation you have these different solutions for each subfield, machine learning is more of it works on operational patterns. So whereas the dominant view is that for each type of verticals where you have different finite element, finite volume or whatnot, classical solvers, you have certain physics principles. So if you try to encode them in a machine learning model, this gets into a nightmare because you have different design principles and the scaling is very, very, very bad. We believe that if you make a data-driven approach fully end-to-end, you can capitalize on the way that basically all simulations or all engineering follows similar design principles. You have a geometry which you convert in some sort of mesh, you solve on the mesh, you run some post-processing. And these design principles and this way of how engineering works is actually more uniform, in my opinion, this is only my opinion, than like physics consistency. So what we try to do is we build these toolings which work for different approaches. And if physics consistency is required, we try to add that in a fine-tuning phase, but not in a conceptual phase. We try to make everything with the same tokenized transformer principles, such that what works for injection modeling also works for geothermal modeling, and so on and so forth. Now, these are the two types of approaches. The left has a lot of academic elegance. The right one hopefully leads to success across verticals. One example of this, and this is the nice way if you have very, very smart students. This is a paper, I think, which was an archive today. We back to weather because weather is very inspirational for me. Michael, Andy, and Florian, they build a modeling paradigm for weather modeling, where what they try to do is to come up with a way that you can train a diffusion model, which you can use for many, many different downstream tasks, basically ad hoc without any fine tuning. This is by basically forcing the model to be physics consistent. And this is something we are exploring because this physics consistence modeling is something which is also very important for many engineering aspects. I explain a bit more what this is doing. So on the left, we have this sort of diffusion forcing training where you input different types of time steps, like where you force the model to predict different types of time steps, which have different noise levels. So you get one clear image of the weather, and then you have to predict 6 states into the future. But all of these states have different noise levels. So you run basically 6 different diffusion processes, and the noise levels vary between these processes. So the model really has to learn to disentangle not only 6 different time steps, but also 6 different diffusion processes. And what this allows you is to use the modern principles of diffusion guidance. And guidance is basically the principle that while running the diffusion process, you can infer in this diffusion process by giving the diffusion some guidance based on the based on the principle or based on the knowledge of giving you a time step t in this diffusion process, what would you predict, and given on these predictions, you correct the diffusion process. So instead of running, so to say, a simple stochastic differential equation, at each time step, you basically correct this stochastic differential equation of the diffusion process by looking up what your process would produce. And with these tricks, you can do many different things. You can, for example, do some counterfactual prediction. So you can force the model to predict what would happen if you were to have a certain temperature across Europe, let's say 2-3 degrees warmer than it usually is. And we did that with predicting some storms, which is quite a funny machine learning exercise. Not sure how interest or how relevant this is, but you can really make a prediction what the weather would be given you enforce a certain temperature. You could force conservation laws, because you always force the model to, in the inference process, to keep a certain temperature or try air mass. You can do downscaling, which means higher resolution for temporal and space. You can do missing data reconstruction and standard weather protection. So we really did a lot of tasks, zero shot with one model, which is trained with this diffusion forcing. I find this quite cool, and I'm actually a big fan of that. So I honestly think that the future of all this type of applications is that you have these big models which are trained to understand these fields without having too much physics guidance. But in the inference process, you can force the models to make precise either predictions which conserve physics or which do other which obey other laws in physics or boundary conditions. Yeah, and since we're talking about this problem scale and basically about physics consistency, what we've done is we've released our framework. So we are very open sourcey, and this is basically the way we orchestrate this way of working across different pipelines. And it's basically building the belief that no matter what type of vertical you're doing, the design principles are always the same. If this is the win, or if this is the way forward, I don't know, but it's something which I consider I'm very excited to explore, because if you can parallelize across verticals in the way you explore these verticals, this will unlock a lot of I would say challenge we have so far, because suddenly it gets much easier to go into different verticals. It gets much easier to also access data and so on and so forth. So if this works, we will see. But if you want, you can have a look at the framework. And the third, and I think most tricky one, is obviously the data. And I would say everyone is far away from cracking that. Everyone produces data in-house, either at the university or at the company. So it's very hard to get access to data. And the way we do this as a company is basically, we realized there's no way to do it in-house. So you cannot generate all the data in-house. So you have to be a bit smart. And actually, the way which works best is to team up with other simulation companies, because they have all the knowledge about data, and you build a model together with them. And that's what we did with this neural model, which I showed you, and which is basically trained on, if you store all the data which we were to produce, it's like 2 petabytes of data, which we obviously heavily subsampled and stored and so on and so forth. So no worries, we didn't store 2 petabytes of data. But you can think of this type of data which we're producing based on their domain knowledge. Similar to this power grid transformer, which I showed you, is like also amounting to a petabyte of data. So we would never be able, unless you hire some super skilled domain expert, to generate the data yourself. In the first step, you really have to team up with companies. And what's also important, it's the software providers who have the the gold nuggets in the hands because they can give you the data you want. So it's a domain knowledge, software provider, and machine learning engineer which make the difference. And there is a very, very big unknown, and I think this is the hardest nut to crack. And that is we do not know, and there is simply no way of having an understanding of how many data it takes for a certain amount for a certain design of experiment. So if you have a parameter setting across which model should generalize, there is no way of basically making a really good estimate what data leads to what performance, and also what type of what's the quality of the data and so on and so forth. So this is a very, very big unknown, and there's very little until no research going into this field, which is a bit frustrating. That is the reason why I sat together with Sid and Neil and basically discussing. I mean, this paper on scaling laws for CFD is basically a discussion we wrote down, going over at least 1.5 years, and it came from the realization that if you start to write down CFD, as we all know, with sort of input-output realization, and then you basically you give some input variables for geometry, some for pre-processing, some for boundary initial condition, meshing, physics, and discretization, and then you write down a few of these typical CFD problems like cars, planes, motorcycles, and all sort of other stuff, and you try to make a guesstimate of how many data you would need, and then you basically try to estimate of how many GPUs hours this would relate to. You quickly realize that there's no money in the world and no number of GPUs which could give you a data set that you can train such a model. And so the first realization is, who claims to have a model which does all CFD? It has a pretty good data set, where it's not clear where this data set is coming from. And therefore, it's very clear that you need to fix a few of these parts. So basically, we started to say, okay, let's fix, for example, turbulence model, discretization scheme, pre-processing, and so on and so forth. And then suddenly it gets a bit, you can get a handle of what to model. And what we try to then estimate what's realistic scaling laws for data model and generalization. And basically there's this scaling laws. I don't go much into them. I mean, you can have a look. I find it very funny because the outcome is a bit like, there's like proper scaling laws, there's like a mathematical derivation. It ends up as always, you have 2-3 parameters, and depending on what values you have, you get totally different outcomes. But the one outcome which is quite interesting is the data generation is super costly. And it seems that there is this one point where model training overtakes data generation. It's just not clear where this inflection point is. And I very much believe that for the next 10 years, data generation will bottleneck AI for engineering, no matter what others keep saying, especially in a field like CFD, where solvers are really, really costly, which is a very good sign for companies like NVIDIA, because this means ultimately also engineers will go to GPUs. And this already brings me somehow to an outlook. I very much believe that this type of, I call them digital engineers, where you give a designer a feedback, is something which in one way or the other is the future. Not saying that we managed to build them, but I believe very much that there will be success stories around that. So basically that any engineer can have this digital twin or this digital friend who gives him or her direct feedback, and therefore makes it easier to design, basically with instant success. One of my most favorite examples, maybe because I'm coming from Austria, Germany, and our car companies are heavily struggling, is crash testing. Because in crash testing is the Achilles tendon of car companies, because it takes quite long for these models to basically get the crash testing right, such that when you crash the car, you get the final check mark that things are done. And this is usually 20 to 30% of this whole design cycle. And each crash test takes quite some time, like usually days from design, from car design, variation in car design to ultimate answer how the crash test would look like, just because the crash test simulation is super tedious. And imagine if you have a model which gives you direct feedback of when you change something in the car, of how the crash test would look like. You could shorten this tremendously, and you would save a lot of time just by getting the crash test simulation right. And instead of wasting a couple of months to get like the crash testing virtually correct, you get it basically within half a day. Not saying that this is happening tomorrow, but it's definitely happening somewhere in the near term future. There is other opportunities like design validation, predictive maintenance, and so on and so forth, which we all hear. I very much believe that there is all these challenges along the way, but with modern tooling and with more access to data and with companies opening up, this is something which we will experience in the next 1-2 years in more or less successful ways. That brings me already to my last slide. This is just a screenshot I put up. I don't know if my co-founders are happy to share that, but I just, everyone can try. This is a demo which we put up today. It's still a silent launch. It's not basically publicly announced, but you can play around in real time how you can design an airplane, a wing of a plane with instant physics feedback. So basically change the wing and you look at the streamlines and all this type of stuff. If the simulation breaks, that is because it's test and beta phase. So don't basically judge me on that. But I thought it would be a nice outlook for the talk because this actually really went live a couple of hours ago. Yeah, with that, I'm very happy to take questions and thanks for bearing with me.
Thank you, Johannes. Well, thank you for the talk. It's been like a very interesting presentation, at least for me. So I think how we're gonna organize now the questions. Anyone in the chat can just raise their hands if they have any questions. Maybe we can start with the room that we have here some researchers in our lab. I don't know if there's any questions in the room.
Sure. I have a question just regarding the fluid intelligence paper. So I'm curious about, because I mentioned this at the beginning when I was introducing myself, but this is for a attention-based model, right? I know there are some guarantees for, I mean, maybe more general models, but can I ask how you think that this would compare against something like mesh graph nets or other, like, I mean, FNOs or another type of architecture, and also perhaps adding in physics constraints versus taking away physics constraints into the model architecture? Because I know there's some ongoing work doing that. Like how would those graphs change, and where would that sort of inflection point between the model training costs and data generation sort of intersect, and how those changes to the architecture would shift the curves a bit?
Yeah, that's many questions. So I would say that if you go to this industrial size data sets, and I mean, you can have a look at the Drive ML data set, for example. The Drive ML data set, I think, has 140 million volumetric mesh cells. There is no way to model that with a graph network. Graph networks break, like from a scaling perspective, if you go beyond 1 million of nodes. It's just very, very, very hard to implement them efficiently on a node, on a GPU. And similarly, other architectures have a very hard time. I don't think that transformer architecture is like superior in a way or can do things which other architectures cannot do. It's just that you can tokenize in a smart way, and it's much more natural how to do this tokenization such that you can use these tricks of transformers. if you really operate on a mesh for graph networks, the scaling is very, very hard. And I wouldn't know how to do a latent representation for these graph networks. So actually, I don't know of any other architecture type which can do inference on like these 100 million mesh cells. And this was a bit the prerequisite how we did the scaling laws. So the way transformer models work is that you have this local aggregation, or this local tokenization, which is like the first principle. And then you end up with a finite number of tokens, which is below 1 million or way below 1 million, and on which you can do self-attention. Can you model this type of problems with graph networks? Surely, but then you would have, then you need some pre-processing and so on and so forth, and this would result in very different assumptions on the storage and so on and so forth, and on the scalability, and it would like be a totally different scaling laws and different data, which I wouldn't know how they look like. So it more or less follows the principle. If we were to use transformers for this type of problems, which showed with recent papers, it's quite a good way to go forward. This is how they scale. Yeah. And secondly, about this physics informed, it's an ongoing debate. I have a very strong opinion on that, and this is a practical opinion that it's just very, very hard to work with physics informed losses. I wouldn't say that physics informed learning per se does not work. I very much think it works, but not in a way that you include it in the loss in the like when you train a big model, because these models are actually very hard to train anyways. And then if you have these conflicting gradients, it gets even harder. But there is this posterior sampling with these fusion models and so on and so forth, which allow you to do this very elegantly. And I still very much believe that when you build these models, they somehow should obey certain physics principles, because otherwise they're very hard to trust. And how to figure that out at scale is, I think, a big research question. And
Thank you.
every company asks us about this. I mean, this is not like an academic question. This is like a real thing.
Thank you. I think we have a question in the chat, and also Chris, I think, raised his hand before. So Chris, I don't know if you want to mute yourself and then just ask the question.
Sure, can you hear me?
Yeah,
Yes, very well.
Okay. Hi, Dr. Brandstetter, enjoying the talk. I actually have a question about, I was just reading a recent paper that you co-authored with some folks at the UK Atomic Energy Authority on gyroswin. The question is basically, for those who don't know, this is a neural surrogate model to model plasmas in a fusion reactor. I understand I understand this in the paper that you train the model entirely on the reduced order models. It was the code, and I understand.
GKW.
Yes, that was the adiabatic electron. Is that by design, or just that is the goal for gyroswin to be able to surmise the missing physics that are averaged out of a reduced order model, or is it just impractical to train it on like a high fidelity model, on high fidelity data?
So it's a good question. So basically, what we said, these plasma simulations, you basically need to model distribution functions, because you cannot track electrons and ions, so you model them as distributions, and then you have like a spatial component and a momentum component and one symmetry degree. So you end up with a 5-dimensional distribution function. And honestly, the main motivation was we want to train a model which works on a 5-dimensional distribution function with relatively high resolution, which is, from a machine learning perspective, quite challenging. The following up work is, and I can say so much, to make this work, like to make this practically relevant, that people can actually use it, which obviously needs to a reformulation of the problem, because like these 5-dimensional surrogates, they are really, really hard and nasty and hard to train and so on and so forth. But we were just very curious of, can we even train a 5-dimensional surrogate? And it turns out that it's really, really hard.
Yeah, I got that. I got that from the paper. Cool. And the one last thing, you said you might be pursuing uh, generative AI, generative methods in the future. Do you think that might include diffusion models?
Yeah, we are heavily training diffusion
Awesome.
models. So there's two types of diffusion models. The first is that you can have, if you train it on like this steady state problems, you can use it for uncertainty quantification, but also for including physics priors, which is some big research we are doing at the moment. It's unconclusive what works best. And the second one is for all temporal problems that you get like consistency over time, which is a super hard challenge. And this injection molding, which I showed, is very linear in a physics perspective, but when you have more nonlinear and even interacting behavior, you need time consistency.
Okay, awesome. Cool. Thank you.
And I think we have one more question in the chat. Sai asks if you can explain a bit more about anchor tokens and what do they represent?
Yeah, so I said before we have this modeling paradigms, and I always had the hunch that physics degree is not simulation degree. Which what I mean by that is in numerics you need these super fine-grained meshes, right? Because if you do not have these fine-grained meshes, you do not get the gradients and you do not resolve turbulence and the simulation is just not converging. Numerics is just not converging. But that does not mean that you need all this tiny information representing in your neural network. In fact, you need some heavy subsampling because you need a way to come up with a representation which has the amount of degrees of freedom that the simulation that the neural network actually needs. And the idea was here very, very smartly from Benedict and Maurits to use tokens which are representatives of surface and volume, and to use only a certain subset of these tokens, which turns out to be a very small subset on the CFD datasets. And then to use this subset of tokens to fully train a transformer in all its glory. But what you can do with these anchor tokens, that you can, if you then select in inference a certain number of points on the volume on the surface, and you run inference with the models on the model, and then you use these tokens to get the weights in the attention matrix, especially the keys and values. You can store those weights, and you can use any other point and run the point basically with a fixed query and value matrix, only fixed key and value matrix, only filling the queries. So in that case, you can get inference on full meshes by choosing a query token which attends to all other anchor tokens, but the anchor tokens itself do not attend to each other. So with each query token, you can increase the complexity linearly. But the anchor tokens span the full simulation, and the anchor tokens capture all the physics. Is this clear? It's a very complicated concept. I'm not so sure if I explained it correct.
Yeah, he just said that he got it. So thank you. And I also wanted to mention just very quickly, there's a lot of people that are very interested on your talk, Johannes, and would like to access the recording after this. And Sujita just posted in the chat the link for the Cassini recordings from the seminar series, so you can rewatch everything. I don't know if there's any more questions. If not, I want to ask you a quick question about the new release that you presented at the beginning of the talk, the large engineering model. How hard would it be to use basically the same framework from a different geometry than the ones that are like already available in the top left that you showed?
Yeah, so we actually trained the model on, I think, 1,000 different geometries, but 990 were synthetically generated. So you could upload any geometry there and it works. So it works across any of these material properties and any of these geometries, which sounds quite cool, and it is quite cool. But I also have to say, and I have to emphasize, that the physics is very simple. Injection molding is linear physics. So it's for us the best problem to start with, because it has a huge variation in terms of geometry, material properties, injection gates. but from a physics perspective, it's super simple. So we had to develop a model which can generalize across all these different things, but still by modeling a kind of linear physics. And usually it's very, very much the other way around, that we have complex physics, but very little variation in flow conditions or geometries. So everyone looks at these variations and says, wow, this is super cool. It is cool, but always under the condition that the physics is linear. So you could actually upload here any geometry. Since we're doing that with a partner, basically they didn't want to see the model break. So we basically, there's a few selected geometries, but it is trained to be very general.
Okay, thank you. And also, I wanted to ask you, in when you develop all of these models, do you use multi-fidelity data, or do you stick with I don't know, like a few degrees of fidelity when you're trying to decide like how to construct your data sets? I know that this is like an open question, but I don't know if you would have any advice on that as well.
I very much like this question. I really think personally that I put it here. How to get these right data sets is a super open question. Multi-fidelity data is a big topic we are actually researching both at university and ME. I don't know the answer. I really don't know. I think if you have a recipe for what data set does it take to train the best model for a problem, that would be amazing. But there's so many components and it's so difficult to nail that down. And it's also so unexplored. So everyone is like very agnostic to data generation, and it's still the most important part here. Yeah, so it's under exploration, but I very much believe in multi-fidelity data.
Okay, thank you very much for answering these questions. I don't know if there are any last questions in the room on our line. Okay, if not, we'll let you go with your newborn because it's pretty late in Europe. Thank you just again for joining us, and yeah, thank you very much for a really, really cool presentation.
Thank you very much for having me. And have a great day.
Goodbye.